So far, we have been thinking of regression models as fitting lines to the underlying data. In order to fit a line, you have to first estimate the slope and the intercept of the regression. As we continue to add more and more independent variables to the model, this way of thinking no longer works. We'll have to start to think of regression models in a different way. From this point onward, we'll lay the foundation for thinking of regression models in a different way, so that we could take this new way of thinking to make sense of more advanced regressions later on. For any regression model, our primary goal is to estimate the true parameters that tell us how different variables are related based on the population sample. However, since the true population sample is usually vast and really hard to obtain, we can only make inferences about the true parameters in the population based on estimated parameters using a small sample. The small sample is collected through a procedure called simple random sampling. In order for the simple random sampling to work, the x and the y's have to be independently and identically distributed or follow an IID distribution. Independent means each small sample is collected independently from the population. That is, no two small samples bear any correlations to each other. Identically distributed means that the small samples are drawn from the same underlying distribution with the same mean and the same standard deviation. In the California schools example, the population of interest is all possible possible school districts in California. The data sample we have used that make inferences for the population consists of 420 California school districts. For each school district, we observe test score and STR, which is a proxy for classroom size. The OLS procedure estimates that the best fitting line looks like this. The intercept is estimated to be 698.93, and the slope is estimated to be negative 2.28. Now, the big question here is, are the estimated parameters equal or close to the true population parameters? And if so, under what conditions and assumptions? In order to make valid inferences for the population parameters, the following three assumptions have to hold for the estimates done by the small data sample. Assumption 1 says the conditional distribution of u's given x has a mean of 0. Assumption 2 says x and y's for all data points in the sample are independently and identically distributed. And assumption 3 says no outliers are likely in the data sample. Now let's make sense of each of these assumptions. Assumption 1 says the conditional distribution of u given x has a mean of 0. This is synonymous to the statement that the conditional expectation of u given x is equal to 0. What this statement suggests is that given x, there is no information left in the residual that can be used to explain the variation in y. Because if there is, then the expected value of u given x should not be equal to 0. This assumption also implies that the other factors in the residual are uncorrelated with x. Because if the correlation is not equal to 0, then the expected value of u given x should not be equal to 0. You can think of it as u given x is not random anymore, and hence these two should be correlated. On the other hand, if the correlation between u and x is equal to 0, it doesn't necessarily imply that the conditional expectation of u given x is equal to 0, because the factors left in the residual, while they are uncorrelated with x, they might still hold explanatory power to explain the variation in y, resulting in expected value of u given x not equal to 0. In the California school example, the only explanatory variable used to explain the variation in the test score is STR. Previously, we have found that the R-square of this regression is only 5%, indicating that STR can only explain 5% of the variation in test score. That means 95% of the variation in test score can be explained by factors still remaining in the residual. The residual could potentially include a host of factors like the following: parental involvement, outside learning opportunities, home environment, family income, etc. These factors might or might not be correlated with STR variable. In the later part of the course, you will see that if any of these factors are correlated with STR, then we have a problem we have to solve. If these factors are not correlated with STR, then we don't worry about it because they don't bias the estimated beta for STR, or in which case is our primary variable of interest. This scatter plot shows that the STR variable on the y-axis does not appear to be correlated with the residual on the x-axis. This scatter plot appears to be relatively random. However, as you will see later, the conditional expectation of u given x is not equal to 0 in this case, and hence the first assumption is violated in this example. This plot goes to show that, again, just because the correlation between STR and u is 0 approximately, does not imply that the first assumption holds. The second assumption assumes x and y are independently and identically distributed. This assumption is mostly a problem for medical science, where data are collected through clinical trials, for example, are based on randomized experiments. In social science, we use observational data, which we can safely assume is always IID. So this assumption is not something we worry much about. The third assumption assumes our analysis sample does not have large outliers. Large outliers in the data is something we should be concerned about, but it's a relatively easy fix. To identify whether there are outliers in the data, we just need to plot the data and see if there are any outliers. This is the data you will use for the quiz. If you plot the data, you will see that Malta is in a different range to the rest of the countries in the dataset. At this point, you might be tempted to remove this outlier, but before you do it, you have to think more carefully about how important this outlier is in the context of your research question. You ask yourself, who is Malta? Why is it an outlier? Is it there because of data entry error, or is it because Malta is a very special country that is very different to the rest of the countries in our analysis sample? If Malta is not important to our analysis, then you could exclude it from the data. But what if the outlier is China or US? Since it's an important country in the world, we might want to include this outlier in our data set nevertheless and run our regression with it. Therefore, outliers are easy to observe, but before you do anything with it, you have to ask yourself the question, how did it occur? Is it a data entry error? Is it something special about an outlier? And by excluding it from the data sample, how would it affect your estimates? This plot shows 4 different data points that you might be concerned about. The orange dot on the top right corner of the plot is an outlier, but this outlier does not affect the regression estimates. Whether this outlier is removed or not, the estimated slope and intercept will remain the same because this orange dot lies exactly on the best fitting line. This orange dot on the lower left corner of the plot is in the data range, so we don't worry about it. we will worry about this data point and this data point. But again, just because they look like a potential cause for concern for us, it doesn't necessarily mean you have to throw them out. You have to ask yourself, why are these outliers there? Is it due to data entry error, or are there anything special about these outliers? Now, please pause this video to take in-class exercise number 6. Assumption 1 says the conditional expectation of U given X is equal to 0. This assumption allows us to think about the regression line as a conditional expectation of Y given X. Let's see what this means. The specification for the one-variable regression is Y given by beta naught plus beta 1 X plus U. Beta naught plus beta 1 times X give us the predicted Y, or the regression line. Now, the conditional expectation of Y given X can be written as conditional expectation of beta naught plus beta 1 X given X plus conditional expectation of U given X. Because the first term is essentially X based on X, so it will just be equal to itself. The second term, given assumption 1 holds, is equal to 0, and therefore it will go away. And therefore, the conditional expectation of Y given X can be reduced to beta naught plus beta 1 times X, which essentially is the regression line. And this way, we can think of the conditional expectation of Y given X the same as the regression line.